So it's recording. Okay, good. Dang it. All right. So if you're joining on Zoom, I'm sorry I missed like the lecture part, but we'll go over it again and again. And dang it, I'm sorry. All right. So we want to print an array. Well, what you need to do the same thing. Pass in our integer pointer A, and then the size of the array. And this is another reason why sometimes we want a class, right? Compartmentalization, everything's together. So we're gonna take the same loop. And instead of loading it up with values, we're gonna say cout. Now this is something you don't normally have to worry about, but we have to double check our work. So actually, I'm gonna start this off as I is 1, I is less than or equal to size. And then I'm gonna do I minus 1 as the index, because I'm gonna say if I modulo 5 is equal to 0, I'm gonna write out an end line. This will give us a tabular look. It won't line up, but it'll just fit on the page better. So we're gonna say print array, I guess array size. Okay, we're good. I was 99.9% sure that we were good, because when you dynamically allocate memory, it allocates it in the heap. And that pointer that gets returned here, and I just haven't done it in a while, because we use classes for everything. That's why I'm trying to switch it up. When I say integer pointer array is equal to a new int of whatever size, it gets allocated in this place in memory called the heap, and it lasts throughout the entire life of the program, unless you delete it. And so when I pass the array up to whatever method, that pointer just has an address in it. So when you start writing to that address and incrementing on that, it should be writing it to the heap, which lasts the entire life of the program, which means we don't have to return anything. And we're good. Okay. Crap, sort, array, size. So then we'll go fix that. All right, so up in crap sort, we need an integer pointer A, integer size. All right, whew, now sorting it. So simple sorts, n-squared sorts, they're easy to implement. Yes, they're slower, but for small data sets, it's so fast it doesn't matter. So we're gonna do a for integer I is 0, and we're not gonna do any improvements on this yet. I is less than size, I plus plus. And then I'm gonna duplicate that loop, and this is what makes it n squared, because we have a nested for loop that's going to process that array. So if my array is 10, I'm gonna do 100 loops. You n squared, now you're starting to be like, oh, this is not so awesome. There's worse. There's n to the n and n factorial, but and there are some optimization algorithms like traveling salesman and optimized like traveling, like hit all the cities in order and come back to this. Those are tough. Even scheduling, room scheduling is an optimization. Those are tough, and they could take long amount of time. But a general way when we sort items is just we compare and swap. We compare and swap. So it's weird how you get used to drawing these things different for different ways. And for sorting, I always go up and down. Stacks are up and down. Let's do 0 at the top. Okay, 8, 3, 2, 10, 11, 15, 21, 30. My random number generator. So let's say I want to go ascending order. So ascending means low to high. So we have two array indexes, I and j. I and j, they both start off at 0. That's probably a waste right there. But that's okay. So the outer loop will start looping. I will be 0. Immediately, the next instruction is start the inner loop. So the inner loop starts running. It sets j to 0. And we need to make a determination. We need to do a comparison, but we don't want to compare to ourselves. So if I is not equal to j, all right, then we'll do something. Okay, so that means the first time the inner loop from on line 7 runs, we'll skip it. Well, we'll skip the if statement on line 8. So it comes back up. I is going to stay on 0 forever. So I is pointing to here for a while. So j goes to 1. So j is right here. And since we're going ascending, low to high, we want to say, hey, is the array A, is A sub j less than A sub I? Yeah, you guys are so smart. Well, we need to do a swap. So let's write a swap. Void swap. This is getting ugly. Integer, pointer A, comma, integer I, comma, integer j. Now this it'll keep working. Well, let's just swap them. So if I is less than j, we're going to say swap I, comma, j. But we need to pass it a as well. Okay. So when you do a swap, there's 3 instructions. That's just a standard typical swap. So we'll say integer temp is equal to a sub I. And then you overwrite that location. A sub I is equal to a sub j. And then a sub j is equal to temp. No return, nothing. That's a swap. Okay. So if we do that, we say, all right, 3, a sub j is 3, is less than a sub I 8. So we call swap and it says temp is a sub I. So over and another on the runtime stack, temp gets a sub I, the 8. Then we overwrite the 8 with the 3. And then we overwrite the 3 with our temp, which gives us the 8. And we have just swapped 2 values. Then j moves to 2. And so we move the j to here. Oh, this is good. I did good numbers this time. I got lucky. So we compare. Is a sub I, where's our code? Oh, we didn't test. If a sub, what did I say the first time? Is if a sub I, no, I want to say j to I. So if a sub j is greater than a sub I, it's kind of like how we said it, right? Then we swap. Okay. So we updated j, and we look at that same if statement. If a sub j, which is a 2, is greater than a sub I, we're still at the 0. We swap them. All right, so the 2 and the 3 would get swapped. Is that good? We just moved the 3, and that seems like it shouldn't be all the way up here, but it's okay, because here's how it's going to end up happening. Let's say down here I had a 1, so a value 1. J is going to walk down this list, and basically your first iteration, the outer loop, is going to find the smallest item and stick it here. So I'm not saying the 2 would, yeah, the 2 would have come up here, because if that's where the 1 was, it would have swapped them. Next iteration, I gets incremented to 1. 0 goes to 1. So I is here the whole time. Then we're going to find the next smallest value and put it. So this isn't bubble sort. This is actually what's called the selection sort. They're both crappy n squared, but selection sort says, go find the smallest item, put it in this right spot. Go find the next smallest item, put it in the correct spot. So next iteration, 2 would end up here. Actually, the 3 would get, but whatever. So all you need to remember is on the outer loop, it's going to start at the very first spot. We find the smallest value. It gets placed. Boom. We march down. We've just found the smallest one. We ignore it, which the code doesn't really ignore it, or does it? So let's make a little bit of an improvement here. Should J always start at 0? Because it really could mess us up. If J keeps coming back to here, and then I is down here somewhere, we might be swapping things that don't need to be swapped. So what we need to do is, like you said, J to I. We could I plus 1, but then we'll just waste. But what that says is, even if the outer loop I is like 0, 1, 2, 3, 4, it's 4 down, then, and we know I, we've got all the smallest numbers done. What's the next one? 8 would go here. We'll swap that in 10. 8, 10. And that's done. So I would be here. Then when we start J again, that inner loop would start over. And when we say J is equal to I, J gets 4. So we jump down here because we don't want to mess with these anymore. They've all been put into their location. So not a bubble sort. A bubble sort would just swap consecutive items over and over and over again. This one goes and finds an item and puts it there. We could, you know what? Yeah, let's do that. What if we found the max value in the or the min value? Instead of swapping, because we still could do multiple swaps. Maybe we only want to swap with the next minimum value. That would save us some instructions. You guys don't look interested. You just want to get to the, okay. Let's test this out first. Hey, are you doing your math homework back there? Just check in. So we said ascending, right? Let's do some smaller numbers. Let's print a print array with a new line. Run. So is this sorted? Yeah. It's just not ascending. How do I fix that? Oh, is it such a huge fix? Can we do it? Boom. Thank God. Yeah, I just flipped the sign.
We told you.
You did? And I didn't hear you?
We said it's a I, but not J.
Oh, okay. So yeah. All right. So we've got we've got a sorted array. And now we can perform our binary search on it. We can use size. No, I just didn't want to pass a bunch of stuff around. But that's lazy programming, kind of. All right, so now we need a binary search. Void, actually, int, because if you find it, you want to return it. Now remember, we're using integers, so look for 88. Here's 88. Yeah, thanks. wow, that was not complex. But it could be a huge record or a file name that contains millions of values, something like that. And then you go find it and return that, and then you process that some more. So yeah, we simplify it, but it's for a reason. So binary search. And we need the same thing. We need integer pointer A, integer size. Okay, so in our binary search, we used at least 3 variables, right? We needed an integer f is equal to 0, integer,
You mean
Uh,
that? All right.
that's what I meant. I had stack or q. We use capitals so they'll read better. Right is equal to size minus 1, yeah, to get started, and then integer m is equal to so we need to parenthesize. Okay, so that'll get us started, and that's an integer divide. So when the assignment happens, it'll truncate whatever floating point is left. It'll get demoted back to an integer. So that's our initial setup. Man, what now? How do I do a for loop? Do I do a while loop? While loop? Okay, so let's add another variable then. Bool found is equal to false. While not found, do stuff. That's always scary to me because yeah, if that you never change that value of that variable, endless loop. But that's whatever, we deal with it all the time. What now? So I know I need to test, I need to calculate left and right, or assign left and right initially, calculate the middle, and then I need to test. The first thing I need to do is test in the way we have the code here, is test to see, is the middle of the key we're looking for? Well, shit, we should probably pass in a key, you think? Okay, so we'll say if A sub M is equal to the key, we'll just say found is equal to true. And then we could, well, shoot, we could return right here. We could return M, the index. And so that's the location. So that would make more sense. Like instead of returning, like if we're looking for 23, returning 23. But if you return the index to that array location, if it did store something important or big, then you would have access to it, let's say. Okay. So if A sub M is equal to the key, we're done. We're golden. Else,
If this m is less than the key, then middle minus 1. No. Then right equal middle minus 1.
yeah, you're on it.
We should change it to else if, right?
So, okay.
Or no,
That-
I
yeah,
guess just do one else and then do 2 different ifs.
Well, let's look at it this way. What are the 3 possibilities? A is less than M, or the key is less than M. The key is equal to M. The key is greater than M. The equal to M is taken care of. So if the key is not greater than M, it's less than M. So if we don't need that catch-all would be fine. But you're not wrong. You're thinking right. All right. So if the key is less than A sub M, we say A sub M, we could do the -1, let's not for right now, is equal to, or I mean, damn it. R is equal to M, right? We're moving the right over to the middle. And then we'll step through this if we have time, because I know just throwing code down and then visualizing it matters. Otherwise, L is equal to M. And we'll do if you're moving the right end, you want to go -1. Otherwise, we want to go +1. Okay. Okay, so if we're in a loop, the loop says, is it found? No, not yet. And then, so we say, if the key at the middle, we're good. We set found to true, which is worthless right now because we're going to return and kill the function anyway. So you literally could put wall 1, and we can maybe change that later. Else, if the key is less than, meaning it's in the left-hand side, because remember, every time we switch, we move right and left, we're eliminating half of the search space. That's why we get log n search time, because, and when we talk about binary trees, it'll make more sense visually. But if the key is less than m, we move the left side over, eliminating that whole half of the array. And then we keep looking. So I now need to recalculate m, right? So down here, I'll say m is equal to L plus R div 2. And we need to parenthesize. So m gets recalculated. We come back up, not found. If a sub m is equal to the key, set found to true, return m. Your car good?
Yeah, it's good now.
Okay. Yeah, he slacked me and said he's going to be late. Thank you. So now, should we just try to run it and see what happens? You guys checking my work? Okay, it never works the first time.
When we say that in a while loop, like we say while not found, then we say while not found, and left is less than right.
Yeah, there's more checks we got to do. Because if it's not in the array, our left and right are going to get messed up. So let's roll back the size to like 10. And then we'll just say modulo by size. No, that might give us duplicates. See, and this is where, like in Python, I could load up an array with sequential data and then just run list.shuffle, and it randomizes it. Anyway, and then you're guaranteed to not have duplicate keys. So I'll stick with, we still might have a duplicate key, but it's whatever. Let's run and see what happens. All right. So a non-void function with a return type. So did I do that here? No. Oh, control may reach end of a non-void function. So this is telling me my binary search doesn't handle every logical path. So we might miss something, but we'll handle it. One thing you could do is just at the very end, return false. So no matter what, it'll catch something. Okay, so is this sorted? Yeah. Do we have duplicates? No. So let's look for, wait, yeah. Array, size, let's look for 421. And then to know if we found it, we need to write out the return value. We're in an endless loop. We missed it. So, damn it. So how do we debug this? I say we draw it out real quick with those same values. We We've got an array of size 10, right? And then we have 335. Can you get 383, 386, 421, 492, 49. And I'll stop there because we're only going to do this half for now. So we set everything up, right? Left is 0, L. Right is size minus 1, 9. Middle is left plus right divided by 2, 4.5, 4. Middle. Bool is when haven't found it. While it's not found, enter that while loop. And on line 47, hey, is a sub middle equal to the key? So let's start with searching for 492, just to see if it does that. Incremental programming. And then you can put in your documentation, only search for 492. Okay, so it found it at location 4. Boom, one case down, we're good. All right, next case. Back to 421. Okay, so this says it's not in the middle. So we drop down next to the else. Is the a sub m, is that less than or greater than the key? So key is 421. Key is greater than this? No. You guys, I mean, I know, I can do this. I need some yes, no. So is our key less than the middle?
Yes.
Yeah, so we go to the else. L is equal to, is this right? Actually, it's there. Is that what we wanted to happen? Okay, so what did I? So if we're looking for 421 and the middle is 492, which way should we go?
We should arrow the right-hand side. The right-hand side should be more far in this case.
We should move this over here, right? Is that what our code says? No, and I don't do this stuff on purpose. You guys know that. I'm just like, so if the middle is greater than the key, now that makes sense when I picture it. The middle is on this side of the key. All right, so we need to move the other way. And that changes the logic for both the else case as well. So now, right, so left is still 0. The original middle is here, 4. And then 421 is less than 429. And so we move the right over. And then we said -1, so here's the right. So based on this data, have we found it yet? So here's another little improvement we could make. If the key is equal to the left, or if the key is equal to the right, or if the key is equal to the middle, that's another couple of constant time instructions. It increases time complexity by a constant amount of time, like 2 more instructions for possibility of killing the program even quicker. So let's do that. So if the middle is equal to the key, so then we'll say else if a sub left is equal to the key. This isn't traditional, right? We're just adding, but it's okay. Else if a sub r, I don't know if my else ifs are right yet, is equal to the key. So if a sub left is equal to the key, found is equal to true, and then, well, return L. If a sub r is equal to the key, we'll say found is equal to true. return R. And so if it's not the middle, if it's not the left, if it's not the right, and then we do another else here, I guess. And then we just, this is in that, the last else, and then we check to see if it's greater than or less than, and we'll adjust. There's still going to be edge cases that might not catch it, so we got to be careful. All right, give me a number to search for. I don't know. I heard of something on a 6, so I'll go 886. So it's an 8. Give me another one. So here's how you test. Like, well, we have edge cases. 335 is the first number in there. Position 0. The last number is 915. You know, or we could say for integer I is equal to 0, I is less than size, I plus plus, and then we take this and we look for array sub I. So we want to say C out, binary search, and then we'll also say I like is equal to, give me some space. That's what my wife said to me the other day. I'm kidding. I need you out of the house. End line, already got end line. So I is equal to I. So now I know what I is, and we know I probably should put a space. And then here we could say, we just tested it for every slot in the array. That's what I was doing. That's like a brute force test. That's probably not good output, but whatever. Yeah, we're good. I think the adding, looking at the left and the right array indexes is killer, because the biggest problem with a binary search is knowing when to stop. Because usually you have to like, is left crossing right, or are they even? But this way you look at your edge cases, and then by the end, left, right, and middle are they're all right next to each other. So you're looking at a 3-slot segment, and you're only increasing your algorithm's time complexity by a constant amount of instructions, which from an asymptotic notation like big O is trivial. Any constant you have in like big O of n, even if it's big O of n times 1,000,000, which I think is bullshit, because that's a big number. But from a complexity standpoint, it's a constant, so you get to ignore it. And there's a lot of things about time complexity and asymptotic notation. There's another concept called amortized time, and I'll have examples for these. But amortized time, so we're going to talk about binary heaps, and a binary heap is we're going to do it in an array, but it's a way to do a priority queue. You know, what's a priority queue? We did one the other day. We ordered values. So if you order based on the priority, the thing at the front of the queue has the highest priority, well, then you built a priority queue. Well, a heap is another way to implement a priority queue. And it's used for a lot of other data structures. So when you do a depth first search, or like Dijkstra's shortest path, you're using priority queues as part of your algorithm to like pick the next place to go. Okay, a Fibonacci heap is a super efficient method for implementing a heap. Now, it's not binary anymore. And we'll get there, but it does a lot of its operations in constant time. So when you're like removing items from the heap, you get constant time performance for a lot of your instructions. Then when the Fibonacci heaps gets out of whack by a certain amount, it does a bunch of operations to get itself back into shape, so to speak. That's the amortized part. It means amortized times means you got to do things for free for a while. And then at one point you got to pay for all that stuff. And I think that's hand waving bullshit too, when it comes to asymptotic notation, because they talk about, oh, you get to access a Fibonacci heap in constant time and it's the best performing. But as soon as it gets out of whack too much, you got to do all those things to get it back. It's like you're still executing a bunch of instructions. So anyway, that's why I think throwing away huge constants is not fair when you're trying to time your code or something. Questions? What time is it? 1:30. We got 20 minutes. Okay. Let's improve our sorting routine by finding the min and the max. Unless you would rather do it as a homework so you can leave now. You're like, that's a tough one. Now let me think if there's something else I could talk about today. Yeah, let me just lecture for just a few minutes. So binary search, and this is what I talked about on the syllabus. We'll jump around a little bit, but it'll come together. So here we have an array-based implementation of a list of values. And in order to do a binary search, we have to sort them, right? And then we can leverage that knowledge to eliminate half the search space every time we do a comparison. Okay, and that gives us, like we said earlier, big O of log n. Okay. The list-based approach to a binary search is to put it in what's called a binary search tree. So I'm just going to draw, just gloss over it. You guys did trees and discrete structures, 1063. I think I got to trees in 1063, but I haven't taught it in a while. So there's, believe it or not, binary tree. Okay, let me get the other one. That green line. Oh, here's there is a list base and there's an array based binary tree. What? Okay. What is a binary tree? A binary tree, well, the definition is a binary tree is a tree is a subset of a graph. A graph is a set of vertices and edges. And all this is going to be in the course notes. So, so a graph is a set of vertices and edges. And a tree is a subset of a graph that has no cycles.
That has no what?
Cycles. What's a cycle? So in a graph, none of these markers work. So in a graph, so these are your vertices, and an edge is just a relationship between vertices. Okay. We're going to repeat all this stuff, but just to get to what I want to talk about. So if I want to traverse this graph, I could start from, let's say, A, B, C, D, E. I can start at node A or vertex A, and I can go to either B or I can go to D. But a cycle, what I want to get at is I can go to A to B, B to D, D to A, and I've just created a cycle. So it's not a tree. So a cycle is if you started a node in a graph or a vertex, and you can get back to yourself, there's a cycle. So a tree would be, are there any cycles in this graph? Can I start at E and get back to myself?
No.
Can I start at D? So the most interesting one is B, because it has what's called a degree. There's an in degree and an out degree for directed graphs, but B's got a degree 3, but you can't get back to it anyway, which is kind of interesting. Everybody else has a degree of, this is 2, and these are all 1. But yeah, a tree is just a graph with no cycles. Okay, well, what makes a binary tree different? A binary tree is just a graph with a set of rules. And it says you can have a vertex, and every vertex has at most 2 edges. Children, really. And then, so we have a left and a right child. Every vertex has at most 2 children. And the definition recursively continues. So, okay. So, basic generic binary tree. This tree's got some properties. All of these down here are leaves. This node here is the root. So when we do a list-based implementation of a binary tree, you always need to know the root. If you don't have the root, you can't traverse the tree. It's like not having the head before you go into a list. All of these are inner nodes. This tree also has a height. The height definition depends on what book you read, but the height of a binary search tree is the longest path from the root to a leaf. This is what we call a nice perfect balance binary tree, but this is also a legal binary tree. It's really just devolves into a linked list. So what we really talk about in computer science when we use binary trees is we enforce some kind of order depending on the algorithm that we apply to this structure. So if we want to do a binary search tree, a binary search tree says that all the values, like values, I'll bring markers next time, less than the root are in the left subtree. Values greater than the root are in the right subtree. So when you look at the absolute root of the tree, everything on this side is less than. Everything on that side is greater than, AKA binary search. So when you look for a key and you look at the root, you're like, hey, is the key the root? Oh, no, it's not. Oh, it's greater. We just eliminated that whole half of the tree, just like we did in the array. Calculate the middle. If it's greater or less than, you eliminate that whole search space. That's where the binary search comes from.
So with that in mind, if you were to write I suppose, like a chain like that, you make the nodes go left and right in sort of zigzag pattern?
You could, depending on the values. What this implies is that everything is greater than the root. And so if there's a 4 and a 6, if I put a 5 in this tree, 5 is greater than the 2, so we go right. 5 is greater than the 3, so we go right. 5 is greater than the 4, so we go right. 5 is less than 6, so we go left. And we throw it in there. So this rule, values less than the root, that's like a recursive definition, because every time you traverse your tree and you go down, new root, new root, new root. So that's how we're going to process these trees, is we're going to use recursive methods, because then the code is simple. The concept, you're like, shit, recursion. But that's all right. This is the best application for recursion. I promise you, it makes the most sense. And because every time you call your recursive method, you're just calling it with pointer to my left child or pointer to my right child, and then all the same rules apply. Like, oh, am I going left? Am I going right? So it's clean. Yeah.
Wait, what happens if you have another one that's the exact same as the next value, Like 2 4s?
So his question was, if you've got two values that are the same, like two 5s, so you're the programmer, you decide, but at the same time, in the real world, we kind of make up our own keys. So a lot of times, even in a database, where a database stores tuples of values, you determine what your key is. So like, some people might just assign a unique value to a set of values just to use as the key. So my answer is, do you want to put the same values in a binary tree? No, but you can handle it. It's just not optimal. So you try to create or come up with values that aren't duplicates. But if it was a duplicate value, based on your code, you can still find it and retrieve it. And that's the thing. When you make a data structure, so this course is algorithms, right? But really, algorithms is just code working with a container. That's it. Array container or list container. You can turn a list into a graph. You can turn an array into a graph. You can turn an array into a tree. You can turn it, anyway. So it's the code running on top of that container that is the crux of this course. So you will just decide, oh, I have the same value. How am I going to handle this to make sure I find it? Because when you create a container of items, you have to be able to traverse it and find stuff. Otherwise, it's a waste of time. So, but you could do it. It just, you don't want it.
Okay.
Okay. What time is it? 7 minutes. We're gonna go over this again, and it's in my course notes, so don't worry, with better pictures and not crappy markers. So we'll probably load up some values into a binary tree, and that's it. And then I'll show you how to do an array-based implementation of a tree next time. So we're gonna just put, okay. So given a list of values, load them into a binary search tree. A binary tree by itself implies no order. It's the binary search tree that implies, just like we had to sort the array, that's what let us do the binary search. They have to be ordered. So we put a 15 into our tree. The root node was null, so we allocated new memory, created a new root. And so you don't see it, but there's 2 pointers here. So we could have a struct, a node with data, and then have node pointer like left, node pointer and right. It's just like a linked list, except instead of 1 pointer, you got 2, one going left, one going right. So 15. Now we read the 7 and we look at the 15 and we're like, is 7 greater than or less than? That's less than, so we go left. And so we take this null pointer, point it to our new value, 7. 17, greater than. 4, less than. 9, less than, greater than. I'm making the tree look better on purpose, but 9, I just did that, oh, 3, okay, now not so good. 3 is less than. Okay, this brings up another term, balanced. A balanced binary search tree is where the height of the left subtree differs by no more than 1 with the height of the right subtree. So left subtree starts here, the right subtree starts there. From here, we're balanced. No longer balanced. And why does that even matter? Because now, since you have a binary search tree, if it's not balanced, you don't get, because a binary search tree gives us this. Without a balanced tree, that starts to degrade quickly. Like when we had it all listed out, that degrades the order in. So another way to write this is big O of H, where H is the height of your tree, because this is now the worst case scenario. Okay, but we're going to talk about how to balance a tree. And if you put values into a tree that are pretty randomly ordered, you're pretty good about maintaining its balance. 2, shit. 80, Okay, so it's 80 is greater than, we go right. It's greater than, we go right. So somebody give me a value that would go here.
60.
Yeah, so it's got to be greater than this one, and there's only one that fits, you're right. And it has to be less than that one, so 16. Is this tree balanced? No. So let's get rid of these for a second. Tree balanced? Okay. This tree is not only balanced, it is complete and full. So this is a full, complete tree. Okay. If I put the 3 back in, it's still balanced, check. It's still complete, check. Not full. So a complete tree just means we add in values. Like if I put in now like a 6, less than, greater than, still complete. So a complete tree just means you fill it in from left to right. Okay, that does not matter one bit of difference right now, but next lecture it'll matter. Okay, all right. Yep, put your seatbelt on, it's about to get on. I love this class. I just feel like I'm getting good at it. I still suck at OOP, sorry. Not really, we still learn some stuff. But I'll do better this semester.
On Thursday, we just print the banner